Welcome to the Deep Dive. We're here to plunge into some really fascinating ideas, hoping you emerge with insights that, well, truly stick. Today, imagine something really quite radical, a fundamental shift in how humanity explores the cosmos. Forget just looking. What if you could actively, shape reality itself?
Okay, let's maybe unpack this a bit. Our current view of the universe, it's incredible, no doubt. But it does face some fundamental limitations. For one, there's the speed of light. We're always seeing the universe as it was, sometimes millions or billions of years ago. That's look-back time.
Right, never as it is now.
Exactly. And then there's the diffraction limit. That's like a fundamental fuzziness, right? Since the 19th century, astronomers have known there's a cap on detail no matter how big the telescope.
A physical limit.
And the biggest mysteries, dark matter, dark energy, completely invisible. We only infer they exist from their gravitational pull on things we can see.
We see the effects, not the cause, essentially. And even testing general relativity, Einstein's theory, in really extreme places, often relies on waiting for rare cosmic events like neutron star mergers. We've only just started detecting those.
Very recently, yes. It's opportunistic science in that regard.
So here's the question. What if we didn't just passively observe all this? What if we could actively experiment with space-time itself?
And that's where this fascinating concept comes in. It takes physics we know, foundational physics, and just stretches it, really pushes it to its absolute limits. It proposes transforming astronomy, from just receiving signals to actually conducting experiments. We're talking about the Gravito-Luminal Engineered Lens, or GLEL.
GLEL, okay.
A groundbreaking idea from Mr. Shahryar Ghiasi. It's pitched as a solution to exactly those limitations you just laid out.
Active space-time experimentation.
That's the core idea. And the central innovation, the really wild part, is harnessing theoretically stabilized neutronium.
Neutronium, like the stuff inside neutron stars.
Precisely. Incredibly dense, degenerate neutron matter. The kind where a teaspoon weighs billions of tons. The GLEL concept involves using this exotic material to build huge, precisely coordinated arrays of microlenses.
Microlenses made of neutron star stuff.
Theoretically, yes. And these arrays would allow us to generate actively controlled gravitational fields. It's a shift from reception to, well, direct experimentation.
Okay, this is definitely deep dive territory. So today, we're getting into the GLEL, what it is, how it might work in theory, what it could do that, frankly, current astronomy can't even dream of, and, of course, the absolutely monumental challenges involved. Get ready for maybe a few aha moments that could reshape how you think about what's possible out there. So where do you even begin? Making something like this, these engineered neutronium microlenses outside a neutron star's gravity. That sounds almost impossible.
It absolutely borders on that, yes. The challenges are, well, colossal. First, you need huge breakthroughs in quantum chromodynamics QCD for these extreme conditions. We'd need to understand how to stabilize and shape matter at densities that are just off the charts. Maybe even using hypothesized things like strange matter.
Strange matter.
Another potential form of superdense, possibly more stable matter. It's still theoretical, but it's part of the discussion for how you might work with this stuff.
Okay, but even if you could make it, wouldn't it just fly apart? The pressure inside must be immense.
Exactly. That's the degeneracy pressure. Mitigating that during fabrication is a huge hurdle. You'd need completely new concepts. Things like theoretical quantum confinement fields.
Quantum confinement fields.
Yeah, hypothetical fields that might subtly change the quantum behavior of the neutronium, helping it hold a specific shape, maybe exotic forces, targeted energy injection. It's very speculative physics.
And then you have to shape it, like machine tools for neutronium.
Essentially, yes. Precision fabrication. Dynamically machining or forming this hyperdense stuff into specific lens shapes, complex curves, gradients to bend space-time just right. It implies incredible control over matter.
Truly mind-boggling. Okay, pillar 1. Make the unmakeable lenses. Pillar 2, once you have them, how do you use them to bend space and light?
Right, that's active gravitational field control. The vision here is a vast array. Thousands, maybe millions of these microlenses deployed way out in deep space.
How far out?
Maybe 500 astronomical units or more, way beyond Pluto to get away from the sun's gravity and other local interference. And the revolutionary part isn't just having them, it's controlling them. Dynamically adjusting the position, the orientation, even the local density gradient of each lens in real time.
What controls them?
Well, that's another massive challenge. It would likely require hypothesized quantum gravity control mechanisms, things we don't have a theory for yet. Think of it like an orchestra conductor. But instead of directing sound, they're orchestrating the fabric of reality itself, bending light, shaping gravity with incredible precision.
Sculpting space-time.
Exactly, creating complex, time-varying space-time curvatures across the whole array.
Okay, so let's assume, hypothetically, we overcome these colossal hurdles. What could this GLEL do? What could we actually see or measure?
Right, the payoff. This is where it gets really interesting. Capability 1, space-time microscopy. Shattering that old diffraction limit we talked about. By actively controlling the gravitational lensing across this huge array, you create an effective aperture the size of your telescope, basically. That could be light years across.
Light years.
Potentially. This gives you unparalleled resolution. We're talking sub-millisecond imaging, enough to directly see details we can currently only guess at, like actual weather patterns, clouds, maybe even continents on exoplanet surfaces. Or seeing the intricate details of gas swirling right around a black hole's event horizon, like Sagittarius A at our galaxy's center.
You could map an event horizon?
With unprecedented fidelity, yes. It would be an incredible test of general relativity in the strong field regime, where gravity is most intense. We'd move beyond the limits of light itself by using gravity as the lens.
Wow. Okay, seeing things is one thing. But you mentioned interacting. This sounds like the real paradigm shift, going from just guessing about dark matter and dark energy to actively interacting with them.
Precisely.
Yeah.
That's capability 2. Direct dark universe probing. It's about interrogating the invisible.
How would that work for dark matter?
Well, you could use targeted subarrays of the GLEL to generate, let's call them controlled space-time modulations, like focused gravitational ripples. You'd aim these ripples at known dark matter concentrations, maybe galactic halos. Then you'd measure how those ripples are affected as they pass through.
Affected how?
Their travel time might change, they might scatter, maybe even be absorbed if dark matter has some interaction cross-section beyond gravity. It would give direct, localized measurements of its distribution, density, maybe even its nature. It's like actively feeling its presence, not just seeing its gravitational shadow.
Okay, that's a leap. What about dark energy? It's even more diffuse, more mysterious.
True. For dark energy, the idea is different. A large subarray could create a very precisely defined, engineered volume of space-time, like a cosmic laboratory box.
A box made of space-time curvature.
Kind of, yes. And inside this controlled volume, you'd place extremely sensitive quantum sensors, maybe matter wave interferometers, devices that are incredibly sensitive to tiny changes in space-time. These sensors would monitor the expansion within that box. By comparing the internal expansion rate to the overall Hubble expansion of the universe outside the box, you could directly measure dark energy's influence.
You could measure its properties, like its equation of state.
Potentially, yes. In a controlled setting. It transforms dark energy from just this cosmological inference into something you could poke and prod in a lab, albeit a cosmic scale lab.
So it's not just for seeing things far away, but literally creating experiments with the universe itself.
Exactly. That leads to the third major capability. Engineered cosmology and fundamental physics. A cosmic laboratory.
What kind of experiments?
Well, you could reverse engineer lensing. Instead of just observing natural lensing, you could configure the array to create a synthetic, ultra-high magnification Einstein ring. Basically, a purpose-built cosmic magnifying glass aimed specifically at amplifying light from the very early universe. Maybe see the first stars, the epoch of reionization, things currently beyond our reach.
A directed telescope using the universe's own light-bending properties.
Precisely, and you could test fundamental physics. Imagine embedding ultra-precise atomic clocks deep within shielded cavities near the neutronium lenses where gravity is intense.
Near the lenses? Wouldn't that be dangerous?
Oh, absolutely. Shielding would be critical. But if you could do it, you could exploit the extreme gravitational time dilation time, literally running slower in strong gravity. And because you can actively modulate the density of the lenses, you could controllably vary the local flow of time for those clocks.
You could turn time dilation up and down.
In a controlled way, yes. That turns the GLEL into an incredible laboratory for precision tests of general relativity in the strong field regime, pushing it far beyond current tests. And maybe, just maybe, reveal subtle hints of quantum gravity.
Wow. Okay. And you mentioned gravitational waves earlier.
Yes, that's another angle. By making the lenses oscillate rapidly and in coordination, the array could potentially generate its own gravitational waves.
Create gravitational waves.
Why? Well, maybe coherent low-frequency signals could be useful for calibrating our detectors or perhaps for entirely new physics experiments using manufactured gravitational waves. Plus, the array itself, being a massive structure sensitive to spacetime ripples, could act as a kind of pre-amplifier or a directional filter for natural gravitational waves detected by other observatories, like the future LISA mission. It could enhance our detection capabilities.
This all sounds absolutely incredible, transformative, but let's be realistic. It also sounds, well, impossible with today's tech or even tomorrow's. What are the biggest show-stopping hurdles here?
You're absolutely right to ask. The hurdles are immense, truly immense. They demand advancements that, frankly, border on the speculative right now. First, as we discussed, neutronium stabilization and fabrication. Just mastering the physics of matter under these extreme conditions, figuring out how to stabilize it outside a neutron star, and then actually shaping it. That requires fundamental breakthroughs in QCD, possibly new physics, and the energy required. Maybe micro black hole power sources, stellar scale fusion. We're talking millennia scale feasibility, realistically. It's a complete paradigm shift needed, not just incremental progress.
Okay, millennia for the materials. What about the control system, controlling gravity itself?
That's probably hurdle number 2, and maybe even bigger. Quantum gravity control. Dynamically shaping space-time like that implies controlling gravity at the quantum level, maybe near the Planck scale. The problem is we don't even have a working, accepted theory of quantum gravity yet, let alone any idea how to engineer systems based on it. This is highly speculative. Its feasibility depends entirely on breakthroughs we can't even predict.
And the power source you mentioned. That sounds like a challenge in itself.
Oh, absolutely. Hurdle 3, energy requirements. Just the energy needed to create, stabilize, position, and control millions of these super dense lenses. It would dwarf the entire energy output of Earth. We're talking energy budgets consistent with a Kardashev Type 2 civilization, one that can harness its entire home star's energy output, or maybe even Type 3, using galactic scale energy.
A Kardashev Type 2 or 3 civilization.
Yeah, so the feasibility horizon based on energy alone is likely centuries to millennia, assuming humanity even reaches that scale.
Okay. Materials, control,
Yeah.
energy. What else? The precision required must be insane.
It is. Hurdle 4, precision metrology and coordination. You need to position these millions of lenses with accuracy, maybe down to the picometer level smaller than an atom, and synchronize their actions down to attoseconds, incredibly short timescales, all across astronomical distances, hundreds of times the Earth's sun distance.
How do you even do that?
It requires revolutionary advances in quantum measurement, deep space navigation, ultra-fast, secure communication. Technologies far beyond what we have. Again, you're likely looking at centuries to millennia.
And finally, just keeping this thing running,
Right.
protecting it.
Right. Hurdle 5, shielding and durability. These lenses would have intense self-gravity. If they use exotic energy sources, maybe Hawking radiation is an issue. Plus cosmic rays, interstellar dust, micrometeoroids. You'd need radical breakthroughs in materials science, maybe exotic matter or energy fields just for shielding and long-term stability. That's another centuries to millennia timescale challenge. So if you connect this all together, these aren't just engineering problems. They require a fundamental rewrite of parts of our physics understanding, plus a leap in our entire civilization's energy scale and technological reach.
Okay, so let's try to wrap our heads around this.
Right.
To recap, the GLEL isn't just a bigger telescope. It's pitched as a fundamental paradigm shift for how we do astronomy, moving from passive observation to active experimentation on space-time itself. And the potential payoffs are huge. Directly probing dark matter and dark energy, shattering resolution limits to see incredible detail, creating cosmic labs to test fundamental physics, maybe even targeted observation of the universe's dawn.
Well, the hurdles are, well, they're astronomical, bordering on science fiction from where we stand today. The GLEL concept does provide a rigorous physics-based vision. It points towards a possible ultimate future for cosmological investigation. It redefines the goal, not just building bigger telescopes, but building instruments that can actively ask questions of the universe by manipulating its geometry.
So what's next for the idea itself? More theory.
Definitely. Future work needs detailed simulations. How would these engineered space-time ripples actually interact with dark matter? What are more realistic models for stabilizing neutronium-like matter? And really developing the mathematics of quantum control, if that's even possible. It's like the blueprint for the dawn of what you might call active astronomy. And this raises a really important question, I think. It challenges us, all of us, to think beyond our current technological boxes, our conceptual limits. It invites us to imagine a future where humanity isn't just a spectator in the cosmos, but an active participant, shaping space-time, understanding its fundamental laws from the inside almost.
So let's leave our listeners with this thought. What does this all mean for you? Consider this. If humanity someday, somehow, achieves the ability to sculpt space-time, what other currently unobservable phenomena might suddenly become experimentable? What else is out there that we can't even conceive of interacting with yet? It's a pretty profound thought about our potential place and perhaps power within the cosmos. Something to mull over. Thanks for joining us on this deep dive.